Alright, let's get started with the next problem of the day. This is LeetCode number 215, kth largest element in an array. Given an integer array nums and an integer k, return the kth largest element in the array. Note that it is the kth largest element in the sorted order, not the kth distinct element. You must solve it in O of n time complexity. This is probably QuickSelect then. Of course, you could do this trivially by sorting it and then finding the kth largest element, but that takes O of n log n time, and we're not including radix sort in there. So, crash course on QuickSelect. This is the partition part of the QuickSort algorithm. The intuition is that we find we pick an element and pivot items to the left or right of it based on its size. And then after we know based on our pivot's position which half we need to continue to partition. So this is like the partitioning part. We just continue to partition the elements without actually properly sorting any part. So that's why we can get this in O of n time. Though I believe it degenerates if you don't pick necessarily a good pivot. Though I don't think that'll be necessarily too important for the context of this. Although you might be able to get like a faster runtime, a faster percentile if you decide to pick like a really smart pivot. And there are ways of picking a pivot such that the runtime is actually like guaranteed to be linear time, or guaranteed to be n log n if in the case of QuickSort. But I think that's a topic for a different video. So that's QuickSelect in a nutshell, and I think this overall makes a decent amount of sense. So let's get started with coding. So let's do this. Let's see. So we're gonna need to have a function to find the kth largest in our integer array between a left value and a right value, and we'll probably still need k, and this returns an int. So this idea is that we can just choose, we'll just say val pivot is equal to our nums on the left side, and we'll say left and right are inclusive for now. And then we'll say, let's see, var left or lesser pointer is equal to, let's see, actually let's do this. Let's make this a little bit easier on ourselves, and we'll say middle is equal to right plus left minus or divided by 2. And this will be the middle part, and our lesser pointer will be on the left. Var greater pointer will be on the right. We'll say while lesser pointer is less than greater pointer. We'll say while lesser pointer, or our nums at that value, is less than our pivot, lesser pointer plus plus, while nums at greater pointer is greater than our pivot, then greater pointer plus plus, or minus minus rather. So the idea is that we will move these pivots. So we start with our pivot at 5, and we'll say while these values, while this value on the right side is greater, then we'll move down, and while this is less then our value will move to the left. And then let's see. So our pivot chosen is 5, and then we want the kth largest. So this is lesser. This is lesser here, but this kind of clears the entire thing, right? And then it'll stop at this element. Let's see. It's been a while since I've done QuickSort. Maybe you can tell by my confusion about this. So then we want to. Do you want to swap it right away? If we swapped it right there, then our lesser pointer would be on the 4. Our greater pointer would still be on the 5. And our lesser pointer then is still less than our greater pointer. And then we moved our lesser pointer there. And this is greater. And our greater pointer is there. So then we move it again. So then at this point we can say val temp is equal to nums at lesser pointer. And then we'll say, let's see, nums at lesser pointer is equal to nums at greater pointer. Nums at greater pointer is equal to temp. So that moves it like that. And then we probably want to do a lesser pointer plus plus, greater pointer minus minus. The problem is that that would move u over here. So this would be on the 4, this moves to the 5, and this would be on the 5 after the swap and move to the 6. But then they'd be overlapping. But the problem is then in that case, if we did something like this, so let's say that there's 4 is here, 5 is here. Let's say that we don't move it. So now lesser pointer moves up because it's less. And then you move here. Now, because the problem is that then in the case that you have a value which is less, or equal to rather, then it might be weird. So let's say that, would that be weird? I think that if we didn't do that and we had pointers that, if we had pointers that were equal to the pivot and we didn't have this moving there, then we'd end up in an infinite loop. The problem then is that we kind of screw ourselves over because then we don't necessarily have the right partition. Let's see. Let's see. Maybe we do something relative to the middle. The idea is that if we pick this middle part, and we pick 5, there's nothing on this side to pivot, And there is one item on this side to pivot, and it's this. And so in that case, well, the problem is that we don't really know unless we say like, oh yeah, okay, if the middle is on the lesser pointer or the greater pointer, then what do we do in that case? Let's see. We can say that if it's, well, if we pick the index and it's, we can say that we assume that it's not in, we assume that it's, the middle will not be in its sorted place. Let's see. Let's say that we moved it there. And let's say that we moved our lesser pointer and greater pointer so that we swapped 4 and 5 and then we don't, and then we leave it like that. So it's 3, 2, 1, 4, 6, 5, right? Then we know that our middle value is now all the way on the right hand side. And since we want the second smallest element, then we need to start from the left hand side all the way back. Then it should be on the left side. But that doesn't seem right. It's like something with QuickSelect here that just doesn't seem right. Hold on. Let me try it out on the second example, and maybe that'll help me out here. So 3, 2, 3, 1, 2, 4, 5, 5, 6. There are a lot of elements here. So this is the middle. So you're larger, larger. You're smaller. So the right pointer goes all the way, or the greater pointer goes there and the lesser pointer stays there. So in that case, if we have that, then do we swap it? In that case, then we have our lesser pointer still remains the same. Our middle is still there, but our greater pointer is still there. But if we have that value, then we should probably modify our starting pivot. So in that case, do we want to change? Do we use this anywhere else? Not really. So let's make this into a var, and then we'll say that if lesser pointer is equal to the middle, then middle is equal to greater pointer. Else, if the greater pointer was equal to the middle, then the middle would be set to the lesser pointer. The idea is that if it was in one of these pointers, then we shouldn't, or then we should keep track of where it is, right? So now our middle pointer is here. And then we move up our left pointer and move down our right pointer. And since this less is still less than right, but this How do I want to do this if I move the element? If I move the middle pivot, or maybe I don't move the middle pivot, but what can I do instead then? Maybe I swap the middle pivot with whatever's on the left. Use that as fodder. So the idea is that rather than swapping the middle elements, what we'll do is that we'll do 2, 3, 2. This swaps here. L, 4, 5, 5, 6. So we swap the 2 and the 1. And now we have something to swap. Right, there you go. And then we do 1, 2, 3, 2 star, 3, 4, 5, 5, 6. And now the greater element is still here, we can say. Because that's greater, right? And then lesser is still here. No, this is fine, this is fine. This is not fine, right? And then we want to swap, so 1, 2, 2 star, 3, 3, 4, 5, 5, 6. Alright, that's sort of the idea of what we wanted to do, where we sort of partition our elements. And if they are on the left or right hand side, so if the middle pivot value is on the left or right hand side at the time of a swap, then shuffle the, well, maybe shuffle is not the correct word, then move the pivot by 1 to the left or right, depending on which half has space. I think that might work, but hold on a second. I'm gonna record this video fairly quickly because it's getting late and I just wanted to get this out here before the end of the day, hopefully. But I was really overcomplicating sort of how the QuickSelect algorithm works. And looking at the Wikipedia definition, looking at some other guides online, it really helped me realize sort of what QuickSelect actually really does in terms of the implementation of it. So it's actually fairly simple, and it's actually something that we've seen before in another LeetCode problem, primarily sort colors. The idea is that while we have a smaller amount, we will swap with whatever we have, or while we encounter a value essentially at our index that is smaller than our pivot, whatever it may be, we will swap it with the next available index, and then we will increment that index. So then from there, we slowly build up a section of elements which are all less than our pivot. At the end, once we finish iterating over the entire array or whatever the subarray is, we will then swap our pivot into the last location of our block that is less. And we have this reference because, well, we keep track of it whenever we swap. So basically the next smallest element would be our pivot. Then we just do the pretty much the same idea. This is something that I had in the code before. And the idea is that we check then to see how far we are within the array. If we are at the point in the array where we expect the index to be, then we know that our pivot element is now the kth largest element in the array, and we can return from there. If not, we can basically run a check to see whether or not we should be on the left side or the right side in terms of the halves that we have partitioned, and we continue from there. because we are running through essentially a log n implementation, and we do this, sorry, there's a way to justify this. I wish that there was an easier way to say this, but because we're not actually sorting the entire array, because we're not performing this step of partitioning and resetting across both halves of the array, our runtime is actually not n log n in the same way that QuickSort would be, but it's actually linear time instead. In any case, I hope this helped, and I'll see you for the next problem.